This
Morning, everyone,
conference will now
and
be recorded.
good morning, everyone, and welcome back to the fifth day of the credit risk modeling workshop. So, what we are doing over here is as per today's discussion, we will be totally focusing on the logistic regression model, right? So, our objective over here would be to understand how is it that the logistic regression model can be developed, and once we have that, following that, we'll kind of explore the other KDB model development and all the other factors. Right. Okay. So over here, we have we are like so over here we have a framework of the logistic regression model, right? So cut yourselves away from all application scorecards, cut yourself away from all behavior scorecards. Just will focus on logistic regression, the way it is executed. So forget all kind of variable selection, weight of evidence, nothing. So we will look into how the model is developed, and given that the model is developed, how is it that the validation happens, right? And how is it that we can decide upon a cutoff score and all these things for the logistic regression model, right? So that is what we are going to talk about in this session. So so talking about logistic regression. Now, so first of all, what exactly is a regression? A regression is a model, it's a mathematical framework, it's a framework which helps us explain the causality in statistical models, right? So in a regression framework, there is always a dependent variable and there is a set of independent variables. Now, one of the most important question that comes out over here is that the base kind of the basic kind of a regression framework that we talk about is always the linear regression framework. Now, if we are talking about the linear regression framework, right, we are kind of talking about a framework where so basically I'm talking about a framework where the dependent variable is a continuous variable and the independent variables are a mix of continuous and categorical variable. Now, from there, one of the important questions that come out is that so if the dependent variable or the target variable is not independent, if it's not a continuous variable, then how is it that you can model that target variable? Now, if you want to model that target variable, like in most of the cases, most of the scorecards that we see, we talk about, so in all the scorecards that we see, we talk about a y equal to 1 and a y equal to 0 kind of a problem, right? So basically, let's say for very simple probability of default models, the y is 1 if the borrower defaults in the next 12 months, y is equal to 0 otherwise. So the dependent variable here is clearly a discrete variable. Therefore, we cannot simply use linear regression in this model. Why? Because in a linear regression model, the dependent variable is a continuous variable. So it can take any values from minus infinity to plus infinity. Therefore, the sum product of the regression coefficients and the variables will result in a continuous value. However, if y is equal to 1 or y equal to 0, it is not possible for us to choose the betas and the x's such that their sum product will be 1 or 0. Now we can do that. Now if we have to do that, that has to be done under very specific conditions. So over here, let's say if I have to make this 1, then only one of the variables, so beta, so everything has to be 0, and beta 1 x1 or any one of the x's has to be should have a value, and that to the reciprocal of beta 1. And similarly, we have to have it at 0, all the variables should be 0. So none of the variables, so either it's a 1 or a 0, but that is not possible for any model to predict, right? Whether exactly a borrower will be a defaulter or not. So we need to design the dependent variable. So that's where the concern with categorical dependent variables coming. Now with categorical dependent variables, it is very difficult for us to predict that y equals to 1 or that y equal to exactly y equal to 1 or 0 using a set of variables which are continuous in nature, right? So it is not possible for you for us to say that the x's and the beta will be chosen such that they'll add up to 1 or they'll add up to 0. Now, so therefore the linear regression framework cannot actually apply over here, because the x betas can relate, or the x betas would relate to a number between 1 and 0, or they will take up any values between minus infinity to positive infinity, right? So, so given this background, given this problem, right, the logistic regression framework, right, starts off with the first objective of converting its dependent variable into a continuous variable. So you have a y equal to 1 and a 0, right? Now your objective or your part is to ensure that this variable is so transformed or is so converted that you have a continuous dependent variable on which a regression can be exercised. So this is the part from where the modeling approach begins, right? So over here, so we now before we go ahead, right? So the way we look into is that how is it that we are transforming from a linear regression framework to a logistic regression framework. Now, linear regression is something which we had studied as a modeling framework when we discussed CCAR, right? So CCAR was seen to be one of those applications of the linear regression models. But however, as we kind of discussed, right? So if the dependent variable is a categorical variable or has to be a categorical variable, then we need to understand the transition that we must have from y equals to, the transition that we must have from y equals to 1 and 0. So the question that comes out over here is that, let's say I have, suppose there is a car dealer, right? So this is a very famous example, and this is where this leads to the foundation of a very famous framework, modeling framework called the linear probability model, right? We'll come back to that linear probability model a little later, right? So where we talk more about the variations. So basically what we have over here is, suppose we have a car dealer, right? And the car dealer wants to identify whether a customer who has applied for buying a car will actually buy the car. So basically whether this particular person actually converts himself from being a lead to being a final customer. Now over here, the first thing that he needs to assess is his buying potential. And let's say the company or the showroom uses, or the car dealer uses, the income of the customer as an index to identifying his buying potential, that actually at his income can he actually afford the car, right? So the independent variable is x. Now if we are using linear regression, how would it be like? So y equals to a plus bx plus e. Now let's say, so now I want to know whether x is 1, or sorry, y is 1 or 0. So that is what I can actually do. Now if I have to estimate that, then ideally I must have a as 0, b as 0.0001, and x as 1000. Now under only this condition can be y equals to 1. Now what if after estimation I get that a is 10? Then how can the model predict? So it is not possible for us to map to a set which has two elements to a finite set from an infinite set. So if you have to map an infinite set in your codomain, in your x variables to y, then y also has to be an infinite set. You cannot do a infinite set to a finite set mapping, right? Because there has to be that mapping would kind of hold under specific assumptions. But otherwise, if the assumptions are not there in place, then the x y would take values which is not there in that set of y. So if your set x is an infinite set and you have to map it to a set y, then that set y also has to be an infinite set. So if x is such a set which belongs to 0 to infinity, or minus 0 to plus infinity, then y also has to be a set which is now y also has to be a set which takes values from minus infinity to plus infinity, right? So so over here, this so in this framework, I cannot use linear regression and OLS to estimate the model parameters, and for that matter, estimate the value of y. So I need something more continuous. So y must be something more continuous for me to predict. I cannot predict only a yes or a no using in this kind of a framework. So either it's yes or it's a no. There must have to be something in between. And that is where people say that instead of estimating 1 or 0, why don't you estimate the probability of y equals to 1 or the probability of y equal to 0? Why don't you do that? Now, now, now this seems to be a good idea, right? That instead of predicting y equals to 1 or y equals to 0, what I am doing is I am predicting probability of y equals to 1 and a probability of y equal to 0. Now, if I am doing this, what are the challenges? Now, again, you see that the set now is not a binary set. Now, this set contains the values from 0 to 1. So, this set now contains fractional values, and it contains infinite fractional values. But the values that this set contains is a set of fractional values, right? So there is a 0 to 1. So there is a so this value is a fractional set of values. Now, if you have this fractional set of values, and now imagine your independent variables x. Now, it is not necessarily that they will range infinitely within 0 and 1. They can end up being values minus 10. They can end up being values plus 1000. So again, mapping from a whole infinite set where the values range from minus infinity to plus infinity, it is not possible for us to map to a set which contains only fractional values, which is 0 to 1, right? So this mapping also does not really work, because even though if it's a continuous mapping between 0 and 1, you are actually mapping a larger set of values of x meters to a y, which is a set of fractional values. So this mapping also does not really work out, right? Now comes the next question. Then how do I solve this? So the question that comes out here is that if I have to solve this problem, I need to make my dependent variable more continuous in nature. And that is where, we kind of we start kind of thinking about the concept of odds. Now, probability y equals to 1 is so basically, if you think about it, probability of y equals to 1 is a fractional value. Probability y equal to 0 is also a fractional value. But if I look into the probability of y equals to 1 to occur relative to that of probability y equal to 0, that need not necessarily be a functional there. That need not necessarily be a fractional value, because let's say probability of y equals to 1, probability y equal to 0 is x, and probability of y equals to 1 is twice as likely as x. So then probability y equals to 1 is 2x. So if you are finding out the odds of the event, then you are trying to find out the odds of the event relative to the non-event. So what you are trying to find out over here is 2x divided by x. If you cancel that out, you end up with 2. So the odds is 2. Now, starting from here, so starting from this point, I can say that if it's the log of odds, right? If it's the log of odds, then you can easily convert this. The log of odds is actually a continuous transformation of the probability y equals to 1 and 0. Now comes the next question. Right? So we can talk about the odds of the outcome. Now, odds is obviously a continuous variable. So what is odds? Odds is nothing but probability y equals to 1 relative to probability of y equals to 0. Okay. So if you observe this odds of the outcome to occur, right? So odds is probability y equals to 1, the probability y equal to 0. So it's the odds. It is how likely is it that the event, or how likely is the event to occur relative to the non-event, right? So odds is something which is always positive, right? Now, when I say odds are positive, what do I mean? So it means that this, because probability y equals to 1 is always greater than 0. So probability y equal to 0 is also greater than 0. Therefore, the ratio is always positive. So this transformation, so this transformation of the variable, the dependent variable, is defined in the interval to 0 to infinity. Right. So what it means is that it is defined between 0 to positive infinity, right? Now, now it is always possible that the x betas on the right hand side they end up as a negative value. So I need to have a transformation which will kind of give me the, so which will help me with the negative, so my dependent, which will help me make my dependent variable range from minus infinity to plus infinity. Now, when we look into the log of odds example, right over here, right? So I can say that it's the odds example. I can say that if I take the log of odds, right, my dependent variable as the log of odds, then this is the then this becomes the linear probability model. So in the linear probability model, the dependent variable is the log of odds. Now this log of odds is log of odds is defined between minus infinity to plus infinity. So if the odds is less than 1, the log of odds is negative. If odds is equal to 1, log of odds is 0. If odds is greater than 1, log of odds is greater than 0. So therefore, log odds transformation helps us make this dependent variable continuous in nature, right? So at this point, what we get to see is that this log odds that I have over here is something which is you know so beta 0 beta 1 x1 plus beta 2 x2 like this, beta k xk. So what I have over here is, so this log odds is the dependent variable. Now log odds ranges from minus infinity to plus infinity, and also the series of beta x will also enter into the, or they also beta x can actually result in a value which lies within minus infinity to plus infinity. So now I'm doing a mapping from a set of infinite set to another infinite set, and this log odds transformation makes this possible, right? So if you want to see this, I'll call this log odds. This is x1 I have typed it as a row vector. This is x, dot, where x is a row vector with all the independent values of x, and b is a column vector with all the values. Okay, so now over here, these estimates B0, B1, B2, Bk are estimated using the maximum likelihood estimation procedure. So now, so over here, what we have is this particular part. Now the next part that I have is that how is it that we can interpret them in the logistic regression framework. So the coefficients are represented as, or they are defined as, the odds ratio. So what is the odds ratio? The odd ratio helps us identify the percentage change in the log odds due to a unit percentage change in one of the variables. So what I want to say is that if x1 changes by 1%, what is the relevant impact on the log of odds? So that is the odds ratio. So when SAS generates the output, right, it generates the output in these four steps. First, it starts off with selecting the variables which are there here, which are put in there. So it does a variable selection exercise of its own using a forward selection method, a backward selection, or using a stepwise selection. So what we generally do is we use a forward selection, a backward selection, and we use a overall selection, a stepwise selection. And using these three, what we do is we run them. We tend to see find the common set of variables, and the variables which are common in terms of these three methods is chosen as the model variables for which on which the logistic regression is to be executed. On the other hand, what also happens is we can also use only the stepwise selection approach. So it is also fairly, fair enough to use the stepwise selection approach and use this stepwise selection approach to get to the final set of variables on which the maximum likelihood estimation is executed, and we get the regression coefficient, the beta zeros. So that is the second set of output that comes out over here, and the third set of output that comes out over here is the log of odds. And then the final set of output which comes in is the goodness of fit measures of this particular estimation procedure. Right? So first it works with the variable selection with the stepwise selection. Then on the selected set of variables, it uses the maximum likelihood estimation. Then on that set of variables, what it does is it uses it does the maximum likelihood estimation, gives us the model, the odds ratio, and finally what it gives us the goodness of fit measures. Right. So that is the general flow of statistics in a logistic regression report. Right. So the key concepts that we need to look out over here are the concept of stepwise selection, forward selection, backward selection. We need to talk about what and how, so what odds are, what odds ratios are, right, and what exactly is maximum likelihood estimation, and so on. So these are the things that we need to look into, right? So the next part over here the next part that we want to do over here is we want to actually use the logistic regression framework. We actually want to use this logistic regression framework and analyze the reports that come out, and we want to see how is it that this particular algorithm is working, right? Okay. So before I move on, up to this point, are there any questions? So you can put, I'll take a pause for a minute. You can put down your questions in the chat box. We'll discuss those questions and then we'll move forward. Okay. So let us kind of look into the methods of now stepwise. Let's now look into the developing the model. Now, when I'm developing the model, so before I we go to develop the model, we just use a set of sample variables, right? And we'll try to develop them. Okay, but before we do that, let's quickly have a look into the German bank data. So that how is it that this data set is and how is it that it can help us in the model development process. Okay, so over here, so the version of this data set, the model development unset, which we are talking about over here. I'll come to this one. So let's start with this data set itself. Now this is the model development data which we use for developing the unsegmented model, right? So we'll just try to understand how logistic regression is there, and then we'll kind of talk about them as well. Now, this is the data set, which is now this data set has kind of gone through 70-30 split, and this is the 70% of the data set, right? And over here you have all the dependent variables over here. You have checking account, you have savings account, you have history, you have loan purpose, gender, residential status, applicant type, property source, and all these different variables. And there and basis the random numbers, the data has been split into two parts: the model development data and the model validation data. So corresponding to model development unset, there is also a model validation unset, right? So you have a model validation unset. So what is your objective over here? What you should do, you should look in over here is that you should try to look into this data, right? And what you need to do is you need to frame an understanding of how exactly the the data works and what exactly is this. So over here, so the validate on the validation data, what we'll do is we'll develop the model on the development data, and once we have iterated on the final version of the model, we'll use that to run it on the validation data and also check out the basic validation parameters, right? Okay, so this is these are the set of the variables that we have over here. Okay. So over here, what I have done is I have specified the model variables in a particular macro, right? So whatever the model variables are at after each stage, we will kind of change the macro and we'll create the set list of all those factors over there, right? Okay. Okay, so before we go on this, before we kind of uh, talk about all these model variables and everything over here. So let's do something. Let's create, I think it's better we create a separate editor window. And over there, we talk about logistic regression separate. We'll use the same set of variables. So that will help us, identify the different kind of iterations that we apply on the logistic regression model. Logistic regression. Okay. So the first iteration, what we'll do is with all the variables that we have with us, right? We will run a particular model. We'll run this model over there. So this is where we have the logistic regression framework. Okay, so now what we kind of look into is the following. The first thing is I want to develop step 01. A logistic model on a the development. Right. So over here I have step 01, which is where I'm trying to develop a logistic model on the development data set. And for doing that, what I have with me is a list of these variables. Now from here, what I need to do is I need to kind of share out, to identify that which of the variables I should be using in the model development process going forward, right? So therefore, there are different ways of selecting the variables, right? Now, one of the ways of selecting this variable is the so the way you want to select the variable, so you can actually specify the way that way can be prescribed is the program itself, and you can actually choose the method. So there are three ways of selection. One of the ways is the forward selection. The second set of ways is the backward selection. And the third set of ways is the stepwise selection. Now, most of the industry practice is to use this, is to kind of use the selection equal to stepwise method. But one of the very important thing is that if you have to choose a final set of variables, before you choose the final set of variables, what you do is you say that uh, fair enough. I'll look into one on the using the forward selection. Then I would look into we'll look into the backward selection, and then I look into the stepwise selection. And from there, I would actually identify out which is the one which is giving me the better set of variables. Right now, the variable set will be those variables which become significant in and retain back in each of these three methods will become your uh, so they will become your most important variables, right? So this is something that we first of all need to explore. Now, as we set on to explore this particular part, right? So there are different ways. Number one is that you need to, so as you go ahead, you need to choose these methods of the variable selection, right? So SAS has, so prop logistic is the procedure that you execute the very details of logistic regression, right? And in this logistic framework, we have the selection method specified, right? By choosing the appropriate variable selection measure, what we generally do is we try to identify that whether the variable is, so how is it that this particular variable is getting selected, right? And what is the best optimal way to select the variables. Now you can extend the variable selection ways in multiple other approaches. So we'll come to that. So before here, we'll first start off with the first approach where we talk about selecting the variables using the stepwise option. Okay, so the first approach that we have is variable selection equal follow using the stepwise selection method. Fine. So before we move on to this, so before we move on to this, is there any questions? Okay, fine. So let's move on. So now what we do is we look into the proc logistic function contains different areas, which we need to understand while working. Okay. Okay, before we start off with this description, right? Just give me a couple of minutes time and just be back and we.
This conference will now be recorded.
Okay. Okay. So welcome back and let's get started with the point where we left it off. So over here, what we were trying to do was we were trying to identify the final set of variables through forward selection, backward selection, and stepwise selection. So our objective over here was to identify, no, that which are the kind of assets or which are the kind of variables which must be chosen. So uh, okay, before I go ahead with the variables, so I'll just give you an idea about the, I'll give you an idea about the structure of the logistic. The proc logistic. So SAS, as we know, has two kinds of steps, right, or two kinds of functions to perform. One of the function is the data step where we create data sets and we create the data sets and we do some data treatments, data preparation, etc. The second is the proc steps where we kind of execute the the procedures or certain statistical procedures over there, right? So this part that we are talking about is a part of the statistical procedures. That is a logistic procedure. Now the so in any procedure step, the way it works is that you have a certain procedure which is there and you have a certain data reference, right? So the objective of the reference data is to ensure you kind of tell you that how is it that you are going to or what is the data on which you need to develop the models and on which that particular procedure is going to be executed. Now we have the DESC option over here, right? So this DESC option, DESC stands for descending. So DESC option ensures that the event is modeled, the probability of the event is modeled, and it is not the probability of the non-event, right? Okay. Now over here, what we have is the model. Now the second part of this code is the model. Now, in any kind of regression step, in any kind of regression activity, so be it your logistic regression or be it your linear regression, you'll always get this part which talks about the model step. So, which gives you an idea about the function that it is modeling something. And in the model step, what you do is you specify the response variable, so the target variable on one side and the independent variables on the other side. Now, if you have a look into this data set, right? So the account ID over here is the ID variable. The checking account, the savings account, the history, loan purpose, gender, residential status, applicant type, property, and all these are the independent variables. And the response variable over here is your, so basically this data set or this response variable is uh, your bad variables, right? So I mean the good or the bad variable. Now the response over here is the way the response is defined for this particular data. The target variable and the definition of the variable is y equals to 1 if the borrower is good and y equal to 0 otherwise, right? And we have specified the method, the stepwise selection to be, or the selection to be stepwise. Now, while we have measured the, while we have discussed that while we have ensured that the selection is stepwise, right? So what we will see is, we'll see how is it that this stepwise selection works, right? And we'll try to kind of reconcile that working with the report that we have over here. So basically this report is based on a separate data set, right? So it is a separate version of the German bank data where we have all the records and all. But given that over here we are kind of looking into the development data, and we want to also validate it and get a more detailed picture of the behavior of the regression model framework. Therefore, I've broken it down into a 70-30 split. So this is a subset of the German bank data, right? With a model development unsegmented data and has some different variables. So the result that you get to see over here is not exactly, the variables that are entered may not exactly be the same, right? So we will look into each of these variables and we'll see how is it that this is done, and we explain each of these steps. So the explanation will remain more or less similar to whatever kind of we have seen over here, right? But what would happen is that just the figures would change a bit, because the figures over here are different figures, right? Okay, so over here, let me run this code. So first what I'll do is I'll run this %let mod var. So this is the macro which is specifying the list of variables that is there in this data set, right? Now, as we go ahead and as the set of variables are transformed, right? As we get to see that if some variables are coming out with dubious signs, some of the variables are coming out with some variables are not really significant, and also so all those variables will be removed, and then the second round of variable selection will be done. Right. So the first thing that we'll talk about over here is, so we have all these variables with us. So there's a checking account, there's a savings account, there's a history, the loan purpose, the gender of the individual, residential status. These are many variables. So we'll run this and let's see how the outcome comes out. Okay. So this is the default outcome of the logistic regression models of the PROC logistic. So at first it will give you an idea about the model development, the data set, the number of observations, records, and everything. So it will give you that whole idea, and then it will give you a summary of the response profile. It will tell you how many goods and how many bads are there. Now, given that you had assigned the DSC option, so your probability model is the response equals to 1. If you had not given this, the model would have been developed for 0 by default. Okay. So this shows the step-by-step entry of the variables. So you can see that at each stage, a new variable is entered into the model. Now, why is it entered? How is it entered is something that we'll talk about. But it is kind of entered into the model, right? And finally, after this, they are entered at each step. Finally, what we have is we have the summary, right? So this summary is our model. So we need to kind of at each stage we need to understand how the variables are selected and which are the variables which are selected, right? Okay. So when we get the variables, the final variables, now this shows the set of variables which was there, and this shows the variable which was selected, and then it shows which was the variable which was removed. So first this variable foreign was entered, and then it was kind of removed. Now, but each of those variables which remain back, what we have seen is the key variables are identified over here, and their word chi-square and their statistical significance is first report. So if I talk about the logistic model at a very high level, this is the model. The analysis of maximum likelihood estimate table is the model, right? And then what we have over here is the odds ratios estimate, which shows the impact that each variable has on the log of odds. And this part gives us an idea about the discriminatory capacity of the model. It gives us an idea about how good the model fit is, right? So the one very important characteristic of the variable selection over here is so one very important select is that this stepwise selection. So at each step, all the variables were included, right? So at each step, it was seen whether a variable was required to be incorporated, and the most important variable was incorporated. Now, the point from where onwards it was not required further incorporation, that incorporation stopped, right? So you will get a certain list of variables with this selection framework. Similarly, when you use the forward selection, you will get some list of variables. And when you use the backward selection, you will get a similar list of variables. Now, the question that comes out here is that what exactly there is a difference between the forward selection, stepwise selection, and the backward selection. So over here, what we'll do is we'll kind of define each of these selection methods. So I'll put this part over here. So it says, so this kind of documents the key notes on the logistic regression on this code that we had kind of written, right? So it identifies the notes on the logistic regression. So it tells me what proc logistic is, what is the DSC option for, what is the model of function there, and why the selection method is there. Now, and after we talked about the stepwise selection, there are two other selection methods. One is a backward, the other is a forward selection. Okay, so now first let's see what are the variables that would come up if on the same set of variables I ran the forward and the backward selection. Then let's compare the variables first and then we'll look into each of their algorithms. Over here, what I'll say is so it is the forward option. Okay. 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 So now I have the forward selection. Okay. So let's have a look into the way the variable is selected in this case. Okay. Okay. So in the forward selection approach, right, only the top few selections are taken, right? So after a point of time, so it is only those top few variables that you are going to take, right? So the number of variables selected over here in now through forward selection is lesser or should be something lesser compared to the stepwise selection or the backward selection. And in the backward selection, what you do is you take out all the variables and then keep on eliminating them basis their insignificance. And in a forward selection, what you do is you select the variables, right, based on their your p values, and just put a cutoff on the p value, right? You don't take variables with higher p values because their impacts are not always statistically significant, right? So over here you will see that, let's say for example, foreign's p-value is more than 0.05, it will be removed, and then again you can kind of develop the, then you can again look for the next set of iterations. But the entire idea is, if you remember, in the selection equal to stepwise approach, foreign was a variable which was removed, but foreign is a variable which is recommended under the forward selection. So over here, so whatever their algorithmic differences are, you can see that they give us different set of variables. So I should run the three set of variables, and from the three, I should chalk out the most common set of variables, and then with those common set of regression, run or another selection approach, right? So, but when I run the selection, so the final selection, it will be the, so when I run the final selections, it will be the stepwise selection. And in fact, it is the overall or the general practice for us to write to, okay. So let's run the backward selection now. So now after we have run the three selections, then we are going to discuss about what their backend frameworks are. So what their backend frameworks are. So over here, what we do is, okay. So over here, see that right at the beginning, the backward elimination process, it inserts all the numbers, it inserts all the variables, and now based on their irrelevance, what they do is, what they do is that they kind of keep on eliminating the variables, right? So in a forward selection, it is only the topmost impacts which are entered. Backward selection, you put in all the variables and then you keep on removing the least significant variables. So the number of variables over here can be relatively larger. And stepwise selection, what stepwise selection does is that at each step it enters the variable and it sees whether it needs to enter another variable or not, and it keeps on doing until and unless the 0.05 criteria is met, right? So all the variables are kind of getting removed over here, unlike what we saw in the selection equal to stepwise approach, right? Age is removed, and finally what happens is you end up with, so these are the effects removed. So finally you end up with this set of variables, right? So the question that comes out here is that are all these three set of variables the same, right? And if yes, how do we proceed with them? If no, so if yes, then what are the common variables? If they are giving now, if they all of them giving the same common variable, then that is fine. However, if they are not giving the same set of variables, then what we need to do is we need to, so then we need to identify from them which is the list of the common variables which are always there in each of the three setups, right? And those common variables are the ones which will be kind of used for the next set of model development. Now on those variables again we'll see what are the signs and everything. But before we go to that, right? So be it the stepwise selection or be the backward selection or the forward selection, we use a similar type of a selection algorithm, right? So what exactly is the logic behind this selection? Fine. Okay. So any questions up to this point? So are there any questions up to this point? So let's start off with the selection equal to stepwise, right? Because mostly, when we are developing our models, we will be looking into the stepwise selection approach itself. Okay, let's first study the algorithm of stepwise selection, right? Now, the way stepwise selection will perform, the way stepwise selection will be dealing with the variables, the similar approach will be followed by both forward and backward selection. So the following matrices will be the matrices of selecting the variables will be the same for both the stepwise selection, forward selection, and backward selection, right? So this is something that we are going to talk about. Okay, so now let's have a look into this. How does the selection begin? In the step 0, so what is entered? The intercept is entered, right? Now, when the intercept is entered, there are two questions that we tend to ask. That is this intercept enough to explain the distribution in the, to explain the observed distribution of the good and the bad, right? So the question that comes out over here is that I need to test the hypothesis over here, right? I need to test the hypothesis that 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 the distribution that is generated with this uh, intercept in the model. So if I develop an only intercept model, can the only intercept model explain the frequency distribution of 1 and 0 that I'm seeing in the model? I mean, that I'm seeing in the distribution, or how good that can explain. So now, if that is the case, the first question that I need to understand is that whether the expected frequency distribution of the good and the bad is equal to the observed frequency distribution of the goods and the bads. So what is your observed frequency distribution of good and the bad in this sample? It is 493 and 210, right? So that is 703. So over here for this data it was entirely 1000, so I use the whole data. So so if I use this model, right, alpha hat only as the model, right, and then I do the sigma transformation and I obtain the probability y equals to 1, and then I assign a cutoff of 1 and 0, will that 1 and 0 that I kind of get from that particular intercept model, will that be statistically, I mean, will there be any significant difference between the observed distribution of 1 and 0 in the data and the 1 and 0 that this model actually scores? So will there be any significant difference in there? So when I say when there is significant difference, now first of all we need to understand, that how is it that we need to find a residual for uh, for our data which is categorical in nature. So where the dependent variable is categorical, in that kind of a data, how is it that I define the, the residual? Because in a linear regression kind of a framework, what we can easily do is we can do a summation, we can actually calculate the residuals by subtracting the predicted minus the actual values. But that is not really possible for us to do for a categorical data where your dependent variable takes two values 1 and 0. So for us over here, the actual or the observed values of 1 and 0 will be the observed distribution of 1 and 0. So this 700 and 300 distribution of 1 and 0. So for the data set that we are using, the base will be like 493 and 210. So that is the observed distribution of the good and bad, right? Now our objective is to check that how close is it that we can get to this distribution of 493 versus 210. So how close can we get to this distribution with our model, right? So that will say that okay, there is no distribution between no significant difference between the observed and the predicted values. Now, as long as this does not happen, we need to keep on trying our iterations and see how best can we get to the observed distribution, right? So this is the first and the foremost check that we are doing. Now, if I see that with the intercept, there is no significant difference between good and bad, then we know that we do not need to put aside any other macro variables. Only if only if the observed and the actual distributions have come close to each other, right? We we don't need to develop any model. Now, if they are different from each other, right, and they are statistically different from each other, then we know that there is always a opportunity to construct a new model and get as close as possible to the observed data set, right? So that is the first step. Now, if this difference is sorted right at the beginning, we'll say that fine, our model is developed. We don't need any other variable. It is only an intercept model which can help us solve that. Right? So that is why when the intercept is first entered into the model, a residual chi-square test is actually conducted. Now, with that test, the p-value is very important because it is this p-value which suggests that whether there is a significant difference in the mean or not. Now, generally what must happen is that the p-value corresponding to this chi-square should be very it should be relatively low. So basically stating that if I consider the differences to be statistically significant, there should be very chances of small losses, or so there would be it says that if the p-value is less than your 0.05, right, so it means that there is still a significant difference between the observed good and the bad and the expected frequencies of the good and the bad in the model. So until and unless that is solved, right, so therefore you cannot say that the model is very representative of the overall population, right? So after you have entered, so the first thing that we must expect is that this residual check after the only intercept check, what should happen is the p-value should be less than 0.01. So it must be very low. So actually the actual probability of committing the type 1 error should be very low. So this is what we have kind of described in the first step. So in the first step, think about it like this, that you have got an alpha hat. Now what you do is you share this okay. So let's say you have this alpha hat. value obtained from the linear regression. Now this alpha hat is something which is intrinsic to the portfolio that you are working on, right? Now, now what you need to do is, this alpha hat is nothing but the log of odds. Therefore, the P can be calculated as e to the power of alpha hat divided by 1 plus e to the power of alpha hat. So that is how you calculate the probabilities, right? And you score each of the actions. Now observe that because alpha hat is just a constant, right? So therefore all the accounts will have the same probability. So if it's greater than 1, it is 0, 1. If it's less than 0, it's 0. So this way a 1, 0 is actually calculated. But given that alpha hat is a fixed component, so if one of the observation flagged as 0, all the others are flagged as 0. So this break between 1 and 0 is not really clear to all. So what we see over here is that as I calculate the probability of alpha hat, right, and I realize that this is going to be a constant flow, right? So the next thing that we do is we know that there is still opportunity to reduce the riskiness and reduce the waste over here. So the next question that comes out over here is that if the observed value of the distribution and the expected value of the distributions are if they have significant difference between the observed and the expected value, or between between the observed frequency and the expected frequency, then we know that there is a new variable which should be incorporated, right? So uh, that is why the second variable needs to be interpreted. Now, now after the first, so once you have entered the way your base 0, that is your intercept model. The next question that I have is that whether the new variable should be incorporated. Now, if the p-value is less than 0.0 less than 0.05, and if yes 0.05, so it means that the second variable needs to be incorporated. So now when we incorporate the second variables, there are there are a set of questions which we need to clarify, right? So before we move on, is this first part, the step 0 of the intercept interview model, clear to us?
Yeah, Tanmay, I just didn't
Yeah.
get how degree of freedom 6 here. How did we identify that?
No, this is output of the this is an output from SAS, right? So of that data, I think had around 7 variables, the one that I worked with, right? So therefore, the degree of freedom was 7 minus 1 6,
Okay, okay,
right?
okay.
So I think that had 7 variables, something like that. So, but the most important part over here to look into this stepwise selection process is the the way it actually models the residuals. The residuals over here is the difference between the observed and the expected distribution, right? And if that difference, as long as that difference is statistically significant, you have to quantitative variables, or yeah, so accommodating new variables which can help us in better distinction of the risk, and therefore the existing variable comes in. So so over here what you have is the explanation of the way this particular process can work. So basically what happens is you score all the record with the intercept only model, that is A star or alpha star. In the second step, what do you calculate the log of odds of that alpha? Now come here for the alpha star, and then you kind of put a cutoff on that, and you capitalize that how many is 1 and 0. And so from there, what you do is you kind of go ahead and you say that there is a difference, right? And hence it should be right. So over here, so once this cutoff is introduced, it will be either good as good or bad. So basically, I'm saying that the given cutoff score, so X has a certain score, Y has a certain score, Z has a certain score, right? Now, now each of these three individuals also had their material, they have their material scores over there. So what happens over here is now from there we'll get the 1-0 flag, right? So now once we do a summarization of this block structure, so once I do the sum, so once I do the summarization uh, of this 1 and 0, right? So one thing that we see that the only intercept model will only score all the records either 1 or 0. So all the records will be 1 or all the records will be 0, and hence there will be a misclassification and that will be captured through the p-value of the classical value of so it will be captured by the logistic regression model, and then we can say that yes, there has been an issue, and this is not only the intercept which can do anything. So from there, we go ahead to incorporate a new variable, right? So just go through this for a minute, and then I kind of continue. Okay, okay. So we look into this. So once we enter the intercept, we look into the chi-square, right? We look into the probability value, and we try to test whether the expected distribution and the observed distribution of the good and the bad are similar or not. So whether there is any statistical significance between the two or not. So if the distributions are not statistically significant, then we say that fine, then I don't need to incorporate any variable. But the question that comes out here is that even scoring all the records with the log odds as a star or the intercept, then the probability y equals to 1 will be a constant estimate for all the records, right? And therefore the count of the 1 and the zeros to be very different also. So it would be the same for all. And hence, in that case, there will be a statistically significant distribution between the actual and the expected. So therefore, more variables need to be incorporated into the module since there are significant misclassifications between the actual and the observed distribution. Now, once we have decided that yes, there exists a misclassification which needs to be corrected, we enter the second variable into the variable. So we enter the first variable first. Now, when you incorporate a new variable, right, there are three things that we need to ask. There are three things that I need to ask. Number one, that is this particular variable helping me reduce the residuals? Now, there are three criterion for computing these residuals. Their calculation is slightly different from each other, and hence the values are slightly different. On the other hand, the intercept and the covariance. Now, if there is a model with the intercept, now if there is a new more variable, there is a new covariant into the model, then the residuals in the model should go down, right? So each of these three measures, the AIC, SC, and -2 log L must show a decrease if your incorporated variable is a good variable. Right? So how do I compute this AIC? So AIC is nothing but the archive information criteria. Now, the archive information criteria has a certain formula. Similarly, the Schwarz-Bayesian criteria has a certain formula. And the log residual, the log likelihood has a certain formula. So it is the two, it is totally the differences which has caused, given the way they are calculated, which has caused the difference in the values. But apart from that, what is important is not the figures in the only intercept model and the intercept plus covariate model. All we need to know is that after the variable has been introduced, does the residual in the model go down substantially? So do see a lower AIC in tomorrow's discussion. So over here, if you have a look into this, that with the only intercept, while there was the only intercept model, AIC had a value of 859. Now, With the intercept and covariance, it is recorded at 784. So what I can clearly say is that the residuals in the model have gone down the moment this new variable has been incorporated. Right? Now, first loss Bayesian criteria, we should do the same thing. In the log likelihood, we should again see a similar thing. Okay. So the first question that we posit is that when a new variable is incorporated, what happens to the residual? Does the residual go down? And whether the residual goes down is captured by the AIC figures. Now the second question is that you have incorporated the variable, the residual has gone down, that's fine. But I don't have a way to check whether the residual has gone down significantly. So what I need to check is that does this variable that you have taken, is that variable statistically significant? Right? Is that variable statistically significant? So over here, we look into these, again, there are these three ratio measures, the log likelihood, the score, and the Wald test, the Wald chi-square test. Now, we will generally consider the Wald chi-square test. Now, over here, what is the question? Over here, the question is that the H naught is beta equal to 0 versus alternate hypothesis, beta is not equal to 0. Right? Now, over here, when you look into this, we say that the Wald chi-square is, so I see that the Wald chi-square is 69.81. So how do we define the Wald chi-square? The Wald chi-square is defined as the beta hat that you obtain from the maximum likelihood estimation divided by the standard error of beta hat whole square. Right? Okay. Now the p-value over here for all the variable is less than 0.001. So it means that it is statistically significant. So the p-value being less than 0.001 means that there is hardly any chance of committing a type 1 error if I want to define this variable as a statistically significant variable. Right? Okay. Now the next question that comes out here is that, so what is the next question that I will ask? That after this variable has been incorporated, do I need to put in any more variables? So what was the first question I asked? That after putting this variable, has the overall residual gone down? So has the observed and the expected frequency distribution come close to each other? The answer is yes. Now the question is, the variable that I have incorporated, is it statistically significant or not? The answer is yes. The third question over here is that after incorporating this variable, do I need to incorporate any other variable? So it has come close to each other, but still there is a difference between the observed and the expected outcome. So is that difference a significant difference? That is shown by less than 0.0001. Right? Any questions up to this point?
And where could we see that the difference is still a significant difference between both the observations? Which test gives us that statistic?
So that is the residual chi-square statistic, right? And if you look into the p-value of the chi-square statistic, you will see that it is still less than 0.001. So it means that, so what is the null hypothesis of this test statistic? The null hypothesis is the observed distribution equal to expected distribution versus observed distribution not equal to expected distribution. So if the expected distribution is less than 0.0001, what it implies is that yes, this in this particular after incorporating the first variable, there is still sufficient residual which can be modeled, because if I reject the null hypothesis, there is a negligible chance of a type 1 error being committed. Hence, there is still more residual which can be modeled, and for that, the second variable duration gets incorporated into the model, right?
Okay, so the first matrix where we say beta equal to 0 is for the variable if it is significant or not, and the second matrix which says residual chi-square says that there is still a difference in both the distribution because we have a
Right.
significant residual.
Right. So
Okay.
there are three things. First, after you incorporate the variable, is the residual going down compared to the intercept model? That's one.
Mm-hmm.
The second is
Mm-hmm.
the variable. So is the answer to that is no, you don't incorporate the variable. If yes, you move to the second question, that is this variable statistically significant? The test that you are doing over there is the beta test, that is H naught beta equal to 0 versus beta not equal to 0. You're using the Wald chi-square statistic, so which is the beta hat pi standard error of beta hat whole square, right? So that is 69.8134 divided by standard error whole square, and you are seeing that whether the p-value of this variable, the p-value of this test is less than 0.05 or not, because it is assumed that we are conducting the test at a 5% level of significance. What you see over here is that yes, this p-value is again negligible. So what it means is that if I reject the null hypothesis of this variable being statistically insignificant, there is a negligible chance of committing a type 1 error, right? So if there is a negligible chance of committing a type 1 error, what it essentially means is that there is, so it means that the variable is statistically significant, right? The next part that we talk about over here is the residual chi-square. So when I talk about the residual chi-square, so now I have incorporated the variable. After this, the next question that comes out to me is that do you think that there is more variable which can be incorporated? So that is where the second set of that's where the residual chi-square test comes in. It says that even after incorporating this variable and after the residual going down, I still see there is a significant amount of residual which still needs to be modeled, and hence the third variable needs to be incorporated. So like this, at each step, a new variable is gradually incorporated. Now, this is considered to be a more optimal method because unlike the forward selection, it keeps on doing it until and unless the chi-square is less than 0.05 and more than, I mean, residual chi, the p-value of the residual chi-square test is more than 0.05. On the other hand, it does it up to the point. It does up to the point. So so it does till that point. Now forward selection starts from there, starts like stepwise selection, but it takes only the 5 or 6 topmost p-values. After a point it stops. It does not do that. So it can bias itself towards the variables of higher explanatory capacity. So variables which are relatively lower explanatory capacity but may be important in the model is left out. Hence, the overall explanatory capacity of the model can reduce. Now, with backward selection includes everything and then keeps on going back based on and keeps on removing the least useful variable. Now, in this case, in this way, it ends up with a larger number of variables. Now, given that it ends up with a larger number of variables, there is always a possibility that it may dilute the capacity of the model. It may, there can be downward bias created by the backward uh, selection. So, out of these two, the middlemost way is the stepwise selection, because it takes the variable one by one, and it does checks and it kind of report the variables, right? So the estimation done in this, because this stepwise selection aims at improving the marginal capability of the model to explain the log odds, right? And therefore there is always a marginal addition it keeps on doing. So therefore this stepwise selection is considered to be by far a much better approach, a much robust approach of selecting the variables, right?
Yeah.
Tanmay,
Yeah, bro.
uh, Tanmay, how do we tell SAS to include the intercept in step like in different forward and backward selection?
So if you do not specify anything, by default it will incorporate the intercept, because the intercept model is the base model, right? And whenever you are computing the log likelihood or the residuals, you are comparing with the model that you have now, the intercept plus the variable model from the intercept model. You are seeing how much of the likelihood the residuals have kind of gone down, because with an incorporation in, so every time you are incorporating a variable, the likelihood function gets refreshed, and the log of that likelihood function will also get right, will also get refreshed. So the residuals. So through the log likelihood function, what do? We differentiate the log likelihood function with respect to the parameters to get the maximum likelihood estimators, right? So therefore, every time a new variable is incorporated into the model, the residuals go down. So the base log likelihood function is your log likelihood with only the intercept. And then as you keep on incorporating the variables into the log likelihood function, you know that this residual is going down. So the difference between the two will actually show me the impact that has fallen on the residuals. Now, how do I define residuals? That as a difference, as a reduction in the misclassification of the observed goods and bads. That is observed frequency versus equal to expected frequency versus observed frequency not equal to expected. Now, if there is still significant residuals which still needs to be modeled, that is where the log likelihood function actually kind of keeps on going up, right? And the p-value shows that it is still significant residual which still needs to be modeled. And if that happens, then the third variable or the next variable gets incorporated over
So Tanmay, in OLS, when we look at the data, so the OLS would give me the expectation of y given x, right? So here it is the log of the odds. We are trying to predict the log of the odds.
Yeah,
but from a data, how do I look at that? Like,
yeah, so the way you look at residuals in an OLS framework and the way you look at an OLS residuals over here is very different. At the OLS level, the residual is actual minus predicted, right? Because both the y values are continuous. Over here, y is categorical. So your residual over here is the difference between the observed and the estimated.
Okay, and the beta would give me here in logistic, the beta would give me still the average effect, right? Like
The
oil.
beta would give you the average, the impact that a unit change in X will have on the variation in Y, right? So how would a unit change in the X variation will impact the Y, the variation of Y? Over here, your beta will give you the odds ratios. That is, how much would a change in this X1 impact the log of odds, or what percentage impact would it have on the log of odds of the dependent variable. So that is the odds ratio estimate, and that impact is shown in the odds ratio table. And in the maximum likelihood estimation table is your model table.
Okay. And is this data set a panel type or is it a cross-sectional one which we are
No,
working
it's
now?
a cross section. It's a cross section.
Okay.
So in a panel
Now,
model,
if it's a panel one,
no. So logistic regression is a purely the cross section data, cross section model method, right?
okay. So for behavioral scorecards, it can be like a panel, right?
No, all these data are cross section data. So the time impact doesn't fall in the data. You append all the data together. The moment you're appending all the data together, so you don't have, you're not actual, you append all the data and then you deduplicate. The moment you do that, the time series aspect is going away from your cross section data. So that moment, from the panel data. So that moment, your variable, I mean, your this thing, tell me, your panel data becomes the cross section data.
Okay.
Because over here you're looking into the average behaviors, right? You're trying to model average behavior at an ID at an account level, not across time. If you want to do it both, then it's a panel data. And this is also not a panel data. The reason is you do that, you stuff your development and validation data, and then you do a random 70% this side, 30% that side. The time series component is one from there, and it becomes nothing but a cross section data. Because if you have to maintain that time dimension, you cannot do a random.
Okay. Okay. So it's basically changed from 0 to 1. That's what you.
Yeah. So all I'm concerned about is the target variable 1 and 0, and how accurately can I predict those records who are 1 and who are 0 based on their different categories, on their behavioral variables.
Okay. So should I sort it 1 together and 0, or just I can put it randomly and run the logistic?
No, 1, 0 is there. So see, I mean, the defaulters and non-defaulters will not occur in an order. Right? In the data, it will appear anyway. So if you want, you can sort it, then you can work with it. If you want, you will also work in a non-sorted.
Thanks.
Right? Okay. Okay, fine. So over here, now see what happens at this stage is, so the way it generally works is, so if you think about it, so when you have just incorporated your intercept, right? And now you want to understand that is your intercept model enough to do all the prediction, and you need to incorporate any other variables. So how will the model work? So the test hypothesis that is there is the expected frequency of the distribution of good and bad is equal to observed frequency of good and bad. So that's the null hypothesis. The alternate hypothesis over here is the expected frequency distribution of good and bad not equal to the observed frequency distribution of the good and bad, right? So that is the second part. So that's the test hypothesis. So H naught versus HA. The next that comes out over here is, now I need to understand why is this so. Okay. So the way it works is, let's say, so first I have the intercept model, right? So with that, so the log odds is there. Now from there, from the log odds, I compute the probability of y equals to 1, right? And then there is a cutoff. So then obviously the cutoff is considered, and then 1 0 1 0 1 0 is distributed. So that's your expected distribution of 1 and 0, and you have an observed distribution of 1 and 0, which is coming from here. Which is coming from here, right? Now when this comes from here, so what happens is, now all your probability accounts are given probability y equals to 1, and let's say the accounts are scored as y equals to 1 or y equals to 0. Now when this account is scored at y equals to 1 or y equals to 0, then if you compare it to the observed distribution, there will be a lot of difference. Why? Because let's say it's classified as good, but all the accounts will be classified as good because the PD is constant. The probability y equals to 1 is a constant estimate over here. So you have 700 and the 300 bads are not actually identified. Now, so therefore, more variables need to be incorporated into the model, because still there is a misclassification. Now, this misclassification is the benchmark misclassification. Now, if the benchmark misclassification is there, so with this benchmark misclassification, I can say that there is more variable to be incorporated. Now, when the first variable is incorporated, again the same exercise is done, right? With the first variable, you have your intercept plus the into duration. You compute the probability y equals to 1, right? You compute the sensitivity, specificity, and you get the cutoff from sensitivity and specificity, and from there you estimate your 1 0 flags, and then the observed and the actual distribution again is mapped, and now you see the extent of misclassification. So when you are doing the actual, so your residual over here is the difference between the observed and the expected frequency distribution. So your residual is the difference between the observed and the expected frequency. So it is, your residual is the extent of misclassification which is happening, and at each stage you want to see whether that misclassification is reducing until and unless at a point of time when the misclassification comes as close as possible to what the observed distribution was, right? So the better your variables are, the more closer this will come. Now when you see that the variables are such selected, now that the misclassification is not very significant, then the model stops selecting all the variables, right?
Tanmay, how did we get the expected frequency here?
So it's by the same approach, right? So you score all your records with this. The py y equals to 1 is calculated, and from sensitivity and specificity a cutoff is identified. I mean, a cutoff gets calculated, and based on that cutoff a 1-0 score is given, and then there is the actual distribution of 1-0 score. You have the expected 1-0, and from there you can check what extent is the misclassification looks like.
Okay, based on the
So it is
cutoff
very
you
much
gave me.
similar to these three. So this is how the algorithm works, because we don't need to do anything. When we run proc logistic, we get the results uh, directly over here. Right. Now, similarly, what happens over here is, so when the new variable is incorporated, so like, for step 2, 3, 4, 5, this will happen. And now one thing that now, how do you assess whether the variables are becoming more and more important or not? What you do is you look into the marginal effect of the covariate. So how is it that the percentage residuals are changing, right? So you see that which are the most important variables. So you see that there is minus 4.74, 5.43, 5.76, minus 3.9 to 4.1. So you see that that at each stage with each variable as it comes in, right, the increase in the residue, the loss in the residual is gradually increasing. Right. So all these variables are kind of given over here, and when each of the variables are being incorporated, only one question is the three questions are always common. First, does incorporating this variable reduce the residuals? Yes. Is the variable significant? Yes. Do I need to incorporate any other variable, or has the residuals gone down significantly? Now, if the answer to that is yes, you stop there. If no, you go to the next variable and you start seeing whether how this variable can be incorporated into the model. So this is how your stepwise selection works. Right now see at a point where like variables, quite a variable has been increased. Now you see that the p-value, so the actual and the expected distribution has started coming closer to each other now. So one thing that you can see is that the p-values have started going more than 5. So now you have more than 5% chance of committing a type 1 error if your this thing is if we incorporate any other variables. So basically that is the reason why foreign was, even though foreign had those kind of removed, right? So one thing that you see, there were 7 variables were incorporated and foreign was removed, and you ended up with 6 variables. Now, more or less, if you do the backward method, right, you will see that you ended up with, I believe you had ended up with your similar 6 variables over here. 1, 2, 3, 4, 5, 7, 8, 6. So with 8 variables. Whatever. So one thing that we get to see over here is that, so one thing that the variables selected by these three approaches are very different from each other, right? So it is not that, these three variables will always be kind of being in the same place. So so if you have to select the optimal list of variables, it is always suggested that you run through the forward step, you do it on the backward, and then what you do is on the forward, backward, and then you do it using the stepwise, and from there you get your final variable, right? So this is how we would kind of look forward to get the final list of the variable from these three approaches. So are these three approaches of variable selection clear to us? Any questions up to this?
Tanmay, so
Yeah, bro.
when we are looking at the model performance, so we will look at the actual and predicted probabilities, or we will look at the probability of defaults, or we look at the expected and like the cutoff after the cutoff.
No. So basically, when you're looking into the accuracy, you will look into the observed and the estimated defaults, 1 and 0. So how accurately have you been able to predict ones, and how accurately have you been able to predict zeros? So you will kind of see from that perspective, right? Okay. So let's take a 10
For
minutes break.
understanding,
Yeah. Yeah. Tell me.
this is just for understanding whether including a variable improves your accuracy in terms of prediction, like in terms of predicting the
Yeah, so basically, if you want to understand whether incorporating a new variable in your model improves the model or not, so what you can do is, after incorporating that variable, right, you can look into the accuracy, and after removing that variable, you can look into that accuracy. Now, if that variable does not add to the discriminatory capacity of your model, right, then it will not be reflected. That's one way. And now the second way is you can develop a model with that variable. Then what you do is you develop a model without that variable, right? I mean, without that variable and with that variable, and then offset the model with the variable that you have the model that you have developed with that variable on the model that you have developed without that variable. So what offset does is, offset will kind of give you the marginal impact of using that variable in terms of Gini and all, right? So that is one exercise that you can do. The offset equation can be used. So we'll talk
and
about
all
offset.
our independent variables. Okay, sure. And all our independent variables here are continuous variables, right?
It can be continuous variable, it can be
Or is there
numerical
a categorical
categorical
variable?
variables. Yeah.
Okay.
Right. Okay.
Now, in this case, like the one which we're using now, everything is
Yeah, so there's a mix of continuous and categorical variables, but most of the variables are categorical.
okay.
Okay, perfect. Okay, so let's take a 10 minutes gap, right? And we'll regroup at around 1:30, and then we'll do it for half an hour more, and then half an hour, 45 minutes more, and then we'll close it for the day. And the remaining part we will complete in tomorrow's discussion. Okay. So thank you guys. Thank you for your time. Let's take a 10 minutes gap and let's be back.
This conference will now be recorded.
Okay. Hey, hi guys. Okay, fine. So let's kind of first kind of see, like, how is it that we can we can start off with the variable selection, right? So how do we do that now? Okay, fine. So let's quickly run these three codes once again, and let's see how the variables appear. Okay, no, I think I have the list of the variables. Variable selection. Okay, so first let's run this code. So this is the this is the one with the stepwise selection. So what we'll do is I'll kind of remove all these variables from here. I kind of don't need these parts. right? So over here you have this. So over here, what I have is I have the summary of the stepwise selection. Right? Now, what we'll do is let's quickly run through. This is the summary of the forward selection. Very variable was dropped. And when you look into the backward selection, this is summary of forward selection. Okay, so over here, what we want to do is, or what we need to do is, we need to check that what are the common variables which are present in each of these three cases, right? So in each of these three selections, and whichever are the most common cases, we are to use them for our development exercise, right? So over here, one thing that you can see is, so obviously one of the variable which is kind of common is checking account. Checking account, right? Now, one of the important variables which the backward selection had actually shown us is savings account, right? But it is not selected, it's not shown exactly by the summary of the stepwise selection and the forward selection. So another variable which is kind of common in all these three is the history variable. Right. Now, similarly, over here, your employment is another variable which is common between all the three. Now, over here, you have other installment rates. So you have this as the, so so these are the set of the common variables that we have with us, right? Now the next part is obvious relationship status, savings account. Okay, duration is another variable which we have, which is common between the three. So for most of the variables, what we get to see is that most of them is kind of common over here, and so you have the checking account, you have the duration, you have the history, you have the employment, you have the other installment rate, and so on. Right. So these are the common set of variables which we will use for developing the model, right? Or we'll use for develop for kind of first of all looking into the first cut of the model. And once that model is identified, right? So once that model is identified, the next thing that we'll do is we'll try to assess. Okay. So the next question that comes, so over here, we'll create a flag. Final verse.
Can we hear history is credit history?
Yeah. History is credit history. So this is a variable which is there which says, you know, who has a delinquent credit history, with a good credit history, who has been a defaulter, and so on.
Yeah.
Right. So then you have so I'll say checking account, duration, so this is history, employment, this is other installment, this is installment fee, and this is, and duration is there already, right? So these are the final set of variables that I'm going to use in the first draft of model. The final verse. We'll put out some other colors. So which are to be used in these. Now these are the red variables which will not be used in this particular iteration. Right. So now with these variables, we set up the second modeling framework. Over here, you see this is approach 2. It says iteration 01. Identifying, developing the model. A logistic model with the common set of variables. Right. So over here, let's say percentage mod bar. So we'll say vars 1. What is the variable that I have over here?
Hello, Tanmay.
Yeah, tell me.
So is it a standard practice to find out common variables among forward, backward, and stepwise selection?
See, many people do it Many don't do it. They directly work with the forward selection. I mean, they mainly work directly with the stepwise selection, right? But I think it is generally better. So once you have done all your variable selection, because see, prior to this, there are also other different other steps, right? So with using which you eliminate variables. Now, whether you want to do a further elimination is depending on the number of variables that you are left with, or the one that you, or the number of variables that you are left with, or it depends on how reliable the variables are. Now, if you see that the number of variables that are being selected by forward backward is very diverse, right? And you want to know that what other variables could be incorporated if any one of these variables did not work out. So for that purpose, it's always better to have a broader repository of variables with you and know that which is the optimal method which is giving you the best result. Now there are people who also use any one of the three methods. They use the three methods and they develop the model and see which one of them is giving them the most robust outcome. So there are different ways people can deal with it, right? So the objective over here for us to understand is just to see all the possibilities which are there, right? Now I'm doing one of the variables with the common variables, right? Now I can one thing that we can do is we can look into those variables, which are there in backward selection and develop a model. We can do it with a set of variables which are there in only the stepwise selection. So there are a lot of different ways in which you can try out multiple iterations to check which is that model which is giving you the best fit, right? So there is nothing like a very industry practice or something, but mostly I'll say 80 out of 100 people, they don't do it. What they do is they directly do a selection equal to stepwise, right? Deepak?
Yeah, okay.
Right. Okay. Now let's have a look into this. And let me run the model. Now the objective is to see how the variables have worked. Okay. So this is the model, right? So one set of variable selection that we have done over here is basis the three approaches. Now, based on this, I have created the second table, right?
And what was the statistic for walled chi-square test?
Ward chi-square is that statistic to check whether the variables that has been incorporated are statistically significant or not. This is the test statistic for testing the statistical significance. So if you want to compute the p-values, right? So there must be a way, right? So there must be something through which you want to compute the p-values. There must be a benchmark or something of the sort, right? So that is the word chi-square.
No, like how did you calculate it? Like what is the formula of Wald?
Okay, so what the word chi-square is beta hat divided by the standard error whole square. So this is estimate by standard error whole square 0.6967.
Okay, so like my so we are using these different methods. Like somewhere sometimes we use F statistic for the residual test,
No,
and here
no,
Wald.
no, never. If statistic is a overall variance test for a linear regression model. It is applicable for continuous variables where you have sum of squares. This is a categorical variable. So Wald chi-square follows a chi-square distribution, right? So the Wald that you are computing over here is being computed. So the beta hat that you are getting over here is an MLE output, right? The T statistic, the corresponding part of Wald for linear regression is your T statistic. So that T statistic is an outcome, so that beta hat over there is an outcome of OLS. So
Mm-hmm.
it is always Wald chi-square which we use.
For categorical.
So Wald chi-square is the statistic used for testing statistical significance of a regression parameter in a logistic regression or in a log of odds regression or in a linear probability model. Right? Don't confuse between the statistics. That is a great blunder.
So it depends on the type of variable, right? I mean, if it is the categorical or it
So
is
the
continuous.
model, so t-test, f-test are exclusive to linear regression framework. Wald chi-square, Hoffman-Emerson tests are the counterpart of T and F in the logistic regression framework.
Okay, sorry,
T and
Wald in
F
which?
cannot T and F cannot be done when the cannot be used when the dependent variable is categorical in nature.
Okay, Wald in which one you said? For the corresponding.
Hoffman-Emerson, the Hoffman-Emerson test, HL test. I'll come to that. We are coming to that. I have not used that. Okay. Now we need to decide whether which of these model variables will be there in the final model, right? And which are the ones which will not be there. Now, how do you do that? So over here, we are introducing two more levels of filters of assessing exactly how would the model be looking like. Intercept is something that we keep, so that is fine. Intercept is okay. No, intercept will be dropped here. Sorry. Intercept is generally kept if the chi-square value is, I mean, if the p-value is statistically significant, I mean, less than 0.05. So this is a pure drop case. Now checking it. Okay. So before I talk about this, about these variables and a keep drop, we need to understand what these values are. So this checking account is nothing but your current account status, right? And this current account status in the data has two values, 0, 1 and 2. So 0 stands for those accounts who are overdrawn. 1 stands for those accounts who have a positive current account balance, and 2 stands for those accounts who do not have a current account. So therefore, obviously, as you move from 0 to 1 and 1 to 2, your chances of being a good borrower increases, right? So therefore, the values of the checking account is positively related to the values of the so to the chances of the borrower of being a good or a bad borrower. So therefore, the sign of the variable is a consistent sign, right? Now you look into the p-value. The p-value is over here is less than 0.001. So what it means is that if I reject the null hypothesis of checking account of the beta corresponding to checking account being statistically insignificant, then there is a negligible chance of committing a type 1 error, right? So this is keep. So therefore this variable is number one. This variable is statistically significant and has a very important has a unambiguous sign. Also, if you look into the world chi-square, the world chi-square is the highest for this variable. So in terms of overall contribution, this variable contributes the highest. So from looking in from all the purposes, and that is the reason why, because of this current account status was there. So this is the reason why this variable has always come up in each of these variables. So therefore I'll keep this variable. Now come to duration. Duration means duration of the credit, right? Now higher, so duration of the credit means you can interpret it like this: so the duration of the credit applied for. Now a borrower who applies for a higher term, higher term, always would have or is expected to have a lower affordability than the borrower who applies a credit for a lower term. So if I'm applying something for a higher term, it means I doubt the fact that I would be able to pay it back in a lower term. Therefore, therefore higher the term of the loan, more risky is the exposure, and hence so it is accepted that the affordability of the borrower is relatively lower, and hence the duration is lower. So therefore this variable is kept back. Now comes history. Now history of the borrower is, as you move from 0, so there are 4 levels to it, right? So as you move from 0 to 3, 0, 1, 2 and 3, you will see that that it moves from being a bankrupt or a delinquent borrower to being a very good borrower, right? So the history, for the history variable, this variable is getting kept back. So history variable also is kept back. Now when we start working with the data, right, over there you will kind of get a deeper look into each of these variables. I'm just kind of trying to introduce these variables to you, therefore I'm kind of giving this. Now let's look into employment. Employment, again, it is positively related. So higher the employment tenure, right? So employment here is employment tenure. Higher the employment tenure, the more stable the borrower is expected to be, and hence greater chances of the borrower of being a good borrower. Now with other installments, higher the other installments are, higher will be the fixed obligation to income ratio, right? And lower will be his probability to kind of lower will be his probability of being a good borrower. And also what you can see is that the variable is a statistically significant variable, right? So what we'll do is we'll put it at keep. Finally, installment rate, higher the installment rate is, higher is the burden on the borrower, and hence lower are his chances of being a good borrower. So therefore I will keep this way. So one thing that I can clearly see is that all these variables are kind of kept back. And what is the object and how is it that I'm deciding over here? So what are the filters that I am providing here? The filters that I am providing here is the unambiguous sign of the variable. So the variable, the sign of the variable must be in line with what the expected and the observed behavior is. And similarly, the statistical significance of the variable. So the variables all are statistically significant and their signs are pretty fine. So one thing that I can see is that the way I had selected the variables has given me variables which are reliable, right? So this is your iteration 1, and this is the first draft of your model that you have obtained. So logistic regression for German bank unsegmented, right? So this is something that we have. Now from here, the fields of exclusions that we have followed here is ambiguity in signs and statistical significance, and it has passed both. So the next stage is to assess it in terms of multicollinear, in terms of association. That is where we define it in terms of the multicollinearity. That's where we see the VIF, right? So let's start off with that part from tomorrow's discussion. So today we started off with the basic idea of logistic regression. We actually explored how the reports are generated, what is stepwise selection, how is stepwise selection done, right? What are the different ways of doing, what is the logic of the stepwise selection, and from there what we have started talking about is how is it that you reach to the final list of the variables, and how do you run the logistic regression, how do you interpret the logistic regression, what what are the important components of the results, and from there how do you derive which are the variables which should proceed, right? So this is something that we are going to continue with our discussion tomorrow, right? And from there we'll talk more about the skip drop analysis, like how many variables are being kept, and how many of them pass the VIF test, like after the VIF test what other tests can be done, and how to assess the overall fit of the developed model. So those are the questions that we are going to discuss in tomorrow's session, right? Okay, and from there we'll also see how is it that the result is validated. After validation, how does it look like, and so on. So first we'll complete the on the development data, and then we'll look into it from the validation data perspective, right? Okay, so thank you guys, thank you for your time, and I will upload the recordings of this week by sitting on today evening, right? Hopefully you should get it from tomorrow morning onwards. Thanks a lot. Thanks a lot for your time. Thanks a lot for spending a weekend with me. And let's reconnect tomorrow. Same time. And let's take it up forward from there. Thank you. Bye-bye. Have a great day. Yeah.
I have a question.
Yeah. Thank you.
Okay, so can you give me the access? I wanted to share something, and there I was having a doubt in SAS actually, coding.
Oh, okay. Okay. I'll give you, just give me a minute. I'll just okay, Oshin,
Sure.
can you just connect me after 7 p.m. today?
Okay, done. We'll do that.
Okay, because I have a session starting now.
Perfect. So I'll ping you at 7 and then we'll connect.
Yeah. Absolutely.
Okay, yeah. Thanks, Tanmay.
Okay.
Yep. Bye-bye.